Hi, in this video, we're going to be talking about big O notation and the performance of algorithms. So to give you an example, if you remember the selection sort that you had in CS 120 or any beginning programming class, they talk about the selection sort, insertion sort, bubble sort. Those have a big O notation of n squared, which means that as the size of the list gets larger, the amount of time it takes to process it quadruples. And there are other sorting techniques such as merge sort and quick sort that are a lot faster because they use recursion. So depending on what algorithm you use and depending on the data that you have to use with that, depends on how much time it takes to run these. We're going to look at an example of a problem to solve to see if two strings are an anagram. An anagram are strings that they have the same number of letters, they have the same letters, but in different orders. I'm just going to type it in here. It's not going to make any sense, but heart and earth have the same letters, just arranged in different ways. Those are anagrams. So we want to look and see if we give two strings, are they anagrams? So we're going to write a program here that's going to do three different solutions to this to see how this works. So to start off with, we're going to import time because we can get the time off the system to set when we start the method or the function, and then when we stop the method, subtract the two, and that gives us how much time it took to run. Okay? And I'm going to also import random because we're going to randomly generate. Actually, I'm going to use numbers instead of letters on this, but they'll still be a string. We're going to randomly generate numbers between 0 and 9 and then check to see if they're the same. Okay, so our first one I'm going to call create string, and this is to create our string. So we can, when we do the testing, we can test different lengths of strings to see how much time it takes to process those. And so I'm going to start off a string equal to an empty string, and then I'm going to run a for loop n number of times. Okay. In this for loop, I'm going to set string plus equals str of random dot randint 0, 9. So we get numbers between 0 and 9. And I have to use the str to convert the number into a string to be able to store it into our string variable. Then I'm going to return, we get done with that, string. Okay. That's just going to randomly create these for us so we can determine if we create two of these, if they're anagrams. And we're going to do it with both of them the same each time so we can test the timing on it on there. And the worst case scenario on this would be if it is an anagram because it has to check every one of them. Okay. So now our first solution that we're going to do, I'm going to call this anagram solution 1. I'm going to pass in string 1 and string 2. And what this one's going to do is it's going to use one while loop to go through and check, or to set it up to be able to check the positions of each one. But it's got to take the first letter of the first string and compare it to each letter of the other ones until it finds a match. And then it goes to the next letter and does the same thing. Each time through, when it finds a match, it will change the second string's character in that position to none. That way we eliminate it out of our list there. Okay, so let me go ahead and we'll get started with this. I'm going to just change one of them into a list. So I'm going to have a list is going to be equal to list of S2. This is so we can make changes to it. You can't change a string. So this is so we can make changes to the characters that are stored in the string of S2. We're going to set position 1 equal to 0, and we're going to set still OK equal to true. So as we're going through this, when we find one that doesn't match, then we know we're done, and we set still okay to false and drop out of our loop. So now, while position 1 is less than the length of S1 and still okay, we're going to start processing this. We're going to set position 2 equal to 0. We're going to set found equal to false. That way when we find one, then we can set it the way we need to. So now, while position 2 is less than the length of our A list and not found, if S1 position 1 equals A list position 2, we're going to set found equal to true. Okay. So once we have a match on there, then we're done looking for that. Okay. So we're going to do else on here, and then on the else, position 2 is going to be equal to, I'm going to do a plus equals 1. Okay. Then we get out of that while loop and we check to see if found, meaning we found it in there, then A list position 2 is going to be equal to none. So we clear that out of there so we don't look for that one again. Okay. Otherwise, if it wasn't found, then whoops, still okay is going to be set to false because we didn't find it in there, which means that it's not an anagram, and then that we can break out of the other while loop. Okay. After we get done with all that, then we set position 1 plus equals 1. When we're done with the whole thing, we return still okay. This is going to return true or false. So that's the algorithm for the first one. We're going to go ahead and do it and test this out down here. We're going to do a main. And the way I'm going to do this is I'm going to set the number for n to a value. We're then going to run through a for loop 5 times and increase n each time through so you can see that how it changes as n increases. So I'm going to set n equal to 1,000. I'm going to print a message here, solution 1. And let me squeeze this down and pull it up a bit higher here for you. And then we're going to do the for loop. So we're going to run a for loop for count in range and run this 5 times. We're going to set string 1 equal to create string passing in n, which would be our 1,000. And then we're going to set string 2 equal to string 1, and then in brackets, colon, colon, -1. And what this will do is it'll start from the end of the string and go all the way through to the beginning. So string 2 will be the same as string 1, only in reverse order. Okay. Now what we want to do is start our time. So we're going to set start equal to time.time parentheses and parentheses. So it's going to pull time off the system, off the computer system, and store that into our variable start. Next we're going to call our anagram solution. So I'm going to call that solution is going to be equal to anagram solution 1. We got to pass in string 1 and string 2. Then once that's done, that's the only thing we want to do then we'll get our time off the system again and store that into end, and then we can print out our results. So we're going to print count, which is the length of string 1, put in a comma, separate it out, a comma, and then time, and then end minus start. Okay. So we'll print out how many we had in our string to compare, and then how long it took to process that. Okay. And then we want to increase, and we're going to increase it. We're just going to double it each time through here. Now I'm going to go ahead in this case and put in a print bracket or parentheses and parentheses to put a space in there because we're going to do 2 more of these in here. Okay. So let's see how this works. I'm going to have to go and save this. So I have to navigate over to where I'm putting my stuff in here. Doing my example test, spring 2025, chapter 2, and I'm going to call this Anagram Test.py. Okay, so let's run this and see if I have any errors in here. Oh, I do have an error in here. Something that I do a lot when I'm creating programs is I forget to put in my main to run it. So there we go. First one took 0.15 seconds. Second one took 0.555 seconds. The third one took 2.1 seconds. And then the fourth one took 8.6 seconds. And this last one's going to take a little bit longer. Notice how it's going up squares, kind of. I mean, it's close. So we have 1, or half, then we have 2, and then 2, actually, that one's more like a cube. 2 times 2 times 2 is 8. And then this one's going to be closer to 8 times 3. I think it's going to be around 24, 25, 6 seconds like that. Well, 33, a little bit higher than I thought. So you can see how much so it's increasing each time through there as the n doubles. Okay. So if we ended up that we had 1 million of these, it would take a really long time to process. So let's look at our next algorithm. Okay. Solution 2 is going to do this a little bit different. It's going to convert both of the lists into, or both of the strings into lists, and then sort those, and then go through one while loop comparing each one. As long as they're a match, it will keep going. Once it finds one that's not a match, it will drop out. So I'm going to put this in here. In here, okay, so this is my anagram solution 2. I'm going to convert both of the strings into lists. So a list 1 will be equal to list S1, and a list 2 will be equal to list S2. Then I want to sort both of these. So a list 1 dot sort and a list 2 dot sort. So now both of them are exactly the same. I'm going to set position equal to 0, and then we'll do and then matches. It's going to tell me if my matches keep going here. Set that to true. Scroll this up a little bit. Then we're going to do our while loop. So while our position is less than the length of S1, and they should both be the same length, or it's not going to be a match at all. So we're just going to assume that, especially in our testing here. And matches. So as we still have matches as we're going through there, then we'll go in here. If a list 1 bracket position POS equals a list 2 position, then position plus equals 1, else matches equals false. So it'll compare each one all the way down through there, the same one and the same one. Since we have them sorted, they'd be in order. And if it's a match, we're good. So we just go to the next one. Once we don't get a match, we know it's not an anagram, so we change matches to false, which will then drop out of the while loop at that point, and then we return matches. Okay. Now we're going to process this one the same way. So what I'm going to do is I'm going to copy this whole thing here and paste it in under here. Okay. I'm going to change solution 1 here to solution 2, and anagram solution 1 to anagram solution 2. The other thing I'm going to, well, let's go ahead and run this one first. Okay, I think I got everything else in here correctly on this. I'm going to run this. And I'll go through the first one. And after this one, we go to the third one, I'm going to change the number in the first one down so it doesn't take as much time to run this on here, because we got to wait 2 more of these. This one's going to be the 8 seconds, and the next one's going to be around 30 seconds. While we're doing that, I'm going to go ahead and resize this down here so you can see it better. Okay, it should be just about done here. Just about done here. Running a little bit longer than I expected, but 30 seconds when you're waiting. There's 35 seconds. And then notice this one here, how much faster this is. Okay. So it took 0.001, 0.001. Those were almost the same for 1,000, 2,000, 4,000 went up to 0.005. 8,000 was 0.008. And 16,000 was 0.01, almost 0.015, 0.14. Okay. So that was a lot faster than this one up here. Okay. So the reason for that is this one is running to a nested while loop. You have a while loop inside a while loop. So this one has a potential of running n times, because it's comparing each one of those. And it does that for this one running almost n times. So that's n squared. When we get down to this one is running n times. Where you have the overhead is in the sort on this one, which we can't tell. I could do this. Let's do this here. I can do start equals time dot time. I don't think this is going to show us much. And then end equals time dot time. And then print and then we can put that in there, if I spell print right, and see what that comes up with. Okay, so let's run this now. Oh, wait a minute. Let's go back down here, and I'm going to change this down to 100, so it doesn't take as long to run. I'll leave the other one at 1,000. Oops, got an error. What did I do wrong in here? I hit an equal instead of a minus on there. Sorry about that. Okay, there we go. So we have sorts with 001. This one is, where's the sorts on here? 001, 001, 005, 008. So the source, it doesn't contribute a whole lot, but it does contribute some on there. And that depends on what sort routine you're working with. If you're working with a selection sort, then this is going to go up really fast. Okay, I don't know what Python uses for its sorting technique, but it's pretty fast in there. But still, that is some overhead on that. So now we're going to look at the last solution. Let me take all this stuff out of here. On here. Okay. The last solution is going to do this a little bit different. Now this one's called the Anagram solution 4, but there is a solution that Anagram Solution 3 that the book talks about if you read the book, chapter 2 in there, and it's brute force, where it creates every possible combination of, say, the letters, and then see if any of them match. You do that for string 2, and if any of those then match string 1. And it's not too bad when you only have like 3 letters, like if you're looking at tin and knit. Okay, it's not too bad because you only have like 8 or 9 that you have to make. But if you have 20, there's like a million combinations or something like that, and it takes forever. It's way too long to be able to do in an algorithm. So we're skipping that one, and we're going to Anagram Solution 4. So in this one, what we're going to do is we're going to set up 2 lists that are size 26. They're going to have the positions for each letter of the alphabet. Then we're going to use a for loop to go through the first string and put or count each one, not count, but take each one of those characters in that string, convert them to a numeric value, and then add 1 to the position in the first list that we created of 26. So what this will do, and actually I need to change that in my program. We're going to change it down to 10 because what we're doing here is numbers instead of letters. And so we're going to use 0 through 9. So if the first character is a 0, then we would add 1 to the 0 position of the list. If it's a 1, we did add 1 to the 1 position. So then when we do that, when we do the same thing for the second list, and then we compare the 2 lists, and if the numbers are exactly the same all the way through, then we have an anagram. Okay? Now, I created my anagram to start with, doing it for letters. And so that's why what I said about having the list as 26 for the 26 letters, but we're doing numbers in the 0 through 9. So we can cut that down to 9 rather than 26 on there. So let's go ahead and I'll see if I can do this without messing it up too bad. We call this Anagram Solution 4 since we're not doing the 3. Okay, scroll this. Okay, so we're going to create C1, and you shouldn't do this stuff in, this is for testing purposes. You should have actual descriptive names on these, but I'm going to do it this way for now because it makes it a little bit easier not having long names. Okay, so C1 is going to be equal to a list of 0 times 26. Oops, we're going to change that to times 9. Okay. And then C2 equals 0 times 9. Now, what this will do is it'll create a list of actually we need to make these 10 because we need 0 through 9. If we make it 9, it'll be 0 through 8. Okay. We need that because that's the numbers we're going to have is 0 through 9. Okay. Now we're going to do a for loop for I in range, the length of S1, position is going to be equal to the ord of S1 bracket I minus the ord of 0. And this is all refers to the ASCII character set. If you remember, in ASCII, every keystroke has a numeric value. Numbers start at 48. 0 is 48. We're just using this. The ord converts the character to the numeric value. So if I is if S1 of I is 2, then we would subtract 48 from the 50 and get the number 2. and that's where we want to store, where we're going to add one to the position in there. So that's what we're going to do here, is then C1 is going to be equal to, C1 DOS, the right keys here, is going to be equal to C1 position plus 1. I could have been did C1 position plus equals C1 or plus equals 1, but I just did it this way on here. Okay, so that takes care of our first one. Then we're going to do another for loop for I in range, length of S2. Position is going to be equal to ord of S2I minus ord of this here. There we go. Ord of 0. So then C2 position is equal to C2 position plus 1. Okay? So if these two strings have exactly the same numbers in them, then we'll know that these match up. Okay? So then what we want to do is be able to go through here and compare these. So I'm going to set another variable j equal to 0. And again, we should use descriptive names, but to help save on typing. Still okay is going to be equal to true, while j, I know there's a j in there someplace. Well, j is less than 9, 10, and still okay if C1 j, and you change this to lowercase here. If C1j equals C2j, then j equals j plus 1. Else, still okay, equals false. And then all we have to do is return still okay. So this one with the big O notation is actually, we have these two are both n, so that would be 2n. This one is an n also, so that would be 3n. And then the other ones here are all constants. We have 1, 2, 3, 4 constants. So this would be 3n plus 1, 2, 3, 4 plus 4. You do away with the insignificant, so you do away with the 4, and you do away with the 3, and so you have a big O of n. Okay. So let's go ahead and get this set up in main. I'm going to do the same thing again. I'm going to copy this. Don't need that there. Okay. And I just need to change my 2 here to a 4 and my 2 here to a 4. I'm going to leave this one down to 100 so it doesn't take as long to run. We already know that that one is a lot slower. Like I'm going to leave the other two at 1,000 there. If I put them down too low, then we don't get any time on them at all. So, and here we go. So this one, like I said, is quite a bit slower, but we have a lot fewer numbers in there. Notice how this one is 0.001, 0.002, 0.006, then 0.1. And then this one down here is pretty much about the same on here. As you can see, a little bit slower, but not much. And the reason for that these two are so close together is because they're both O of n. Okay? Anagram 2 has a single while loop that has a potential of running n times, and solution 4 has one. It actually has three for loops. Or I'm sorry, three loops, two for loops and a while loop. Each of them running n times. Okay, so pretty close to the same thing on those. But that gives you an idea of how important it can be to analyze your algorithm to see if there may be something